So our speaker today is Zuofu Cheng, who's a lecturer here at the university and has been doing these. Well, you're gonna give demos.
Yeah,
there's really cool stuff with synthesizing reverberant spaces.
Yeah. So my talk is called Design in Real Time, GPU accelerated acoustic simulation engine for interactive applications. And really, interactive applications just means games. It's easier for us to say interactive applications because people like to think, oh well, this could be used for simulations and this could be used for other things. But primarily I'm concerned about making games sound better. So I'm Zuofu Cheng. I'm a lecturer here. I got my PhD here over the summer. So I'm kind of a new member here, but I've been here for a while. So let's go ahead and get started. And so there's a little bit of context for it. Sound in modern games. So let's just kind of go ahead and just kind of jump right in and give a little bit of context for what current systems look like. So there's a lot of middleware out there for games. So if you have an idea and you're going to go and make a game, you're going to make the next Daisy or whatever, like really big, viral Kickstarter hit that's going to make you millions of dollars, your next Minecraft or whatever. Most likely you're going to use one of these engines. Fmod, Wise, and then the newcomer in the field is RealSpace 3D. And so these engines, pretty much the way they work is they're kind of like recording studio software. So I don't know if anybody's been in a recording studio, but the general idea is what you want to do is, okay, so let's say we have some sound effects that are recorded, right? We have some sample clips. And then we put them into various tracks, and then we hook up the tracks to various game events. So for example, if your character is jumping, then he should make one of these 5 sounds, right? And if he's shooting, then depending on the reverberation tag that's the room that he's in and the room the monster's in or whatever, then it should go through this effects chain and it should sound like this. So really, like existing systems, they operate as kind of recording studios. So they're just dynamic recording studios that are being driven by game effects. So the way you think about this is, imagine there's a really good guy who's in the recording studio, and he's really looking at the game, and he's twisting all these knobs, right? He's twisting all these knobs fast enough to react to the events that are in the game, but that's how that software essentially works, okay? So there's no physical simulation going on. You can, for example, do some neat things, like for example, let's say there's something happening in the other room, and we want to give the player a little bit of a hint that there's something happening in the other room. So what we do is we make a track that's audio from the other room, and then we would send that through a filter, maybe have a different reverb, give that a direction, which is the direction of the door, and go ahead and trigger that to whenever the enemy or whatever is in the other room. So these are essentially parametric systems, right? And what we want to do is we want to get away from that parametric model. So this is exactly what I was talking about before, right? So we have some things, we have game state, we have maybe geometry, and then we have the actual audio sources, the samples themselves, and we derive a bunch of parameters from the game state. And you can think of this as the knobs that the guy is twisting in real time, right? The engine is twisting. And then the engine, whatever this is, either Fmod or Wise or whatever, is going to go ahead and do all the DSP. And usually it's done by software these days because computers are pretty fast for a couple of audio streams. So usually that's done by software. And it's going to do, for example, the low-pass filtering in the situation I just talked about, or the reverberation, the emulated reverberation, so on and so forth. So a key here is that the game state really doesn't directly interact with the signal processing ever, right? It's always deriving parameters, which are then fed into the signal processing side, okay? And so that's our traditional kind of parametric model for game audio. What we want to do, though, is we want to kind of look at a more physically derived way of generating game audio. And this is what we mean by a simulation method. Okay? So what we're doing is we're actually taking the geometry, taking, for example, the acoustic materials, taking the recordings themselves, throwing everything into a simulation, right? In which case we're using a ray-based simulation, and then generating the audio from that. Okay, so there's a key difference because in our case, we're not deriving easily enumerable parameters from the game state. It ends up being very difficult. Like for example, there's some problems with this, right? Like if you have a hole in a wall, right? Normally that wouldn't affect a traditional based simulation because it would just ignore it. You wouldn't have any problem with that. But if you had a hole in a wall here, or let's say your level was just out in space or something crazy, well, you wouldn't get any audio at all, right? But the advantage, of course, is we can have more direct coupling of the gameplay state to the actual audio, right? And that's what we want to do. We want to increase the immersion and the interactivity of the audio space, just like we do with the game, with the graphic space. For example, like a big example of this is physics engines, right? So it used to be traditionally that animations, in the game for the game models were derived traditionally. So they were recorded animations, either an animator went in there and manually tweaked the limbs or whatever, or they were motion captured, so on and so forth. And certain game events would trigger the right animation, right? So you would say, maybe if you have a football game, someone's tackling, well, he would trigger one of the 5 tackling animations. Lately, there's been kind of a push to, instead of having these predefined animations and these parameters that play the correct animation at the correct speed, so on and so forth, there's been a push to physically simulate the animations with a physics engine. Right? You could do that. You could give some constraints to the way the human limbs can move and so on and so forth, and you could do some kind of physical thing to simulate a tackle rather than play back a recorded tackle, for example, in a sports game. Right? This is the same thing, except for audio. So let me just go ahead and play 2 examples. The first example here is from a game called Stalker, and it's a couple years old. And this is kind of sort of the par of the course, even for kind of modern games here. So you have some basic positional audio, which is rendered through OpenAL, which is a hardware engine. But there's almost no environmental dependence. There's almost nothing going on here where the gameplay really interacts with the audio any more than playing the correct sound effects at the correct time. So just kind of listen, and there's a couple of things that are pretty obvious about this video. So a couple things to notice. For example, when he's shooting outside the sewer pipe, right, it sounds exactly the same as if he's shooting inside the sewer pipe. It's playing the same audio, right? And if you were maybe had more of an audio budget, and if you were like a AAA game that had, that has $100 million of budget, maybe you would have somebody say, okay, well, when he's inside the sewer pipe, let's just pipe that through a reverb. So it sounds a little bit better, right? But typically, game audio is not simulated. So this is the kind of result that you get. The explosion really sounds the same no matter where it is. Yeah, there's some, if you listen carefully, and it's hard to do with these speakers, but if you listen on headphones, you can tell there's actually, the positional audio is not bad. So you can identify which direction that explosion is coming from. But it sounds like it's in free space, even if it's indoors, with respect to like outdoors, for example. So let's take a look at our engine, and I'm just gonna, I just wanted to put this slide up because this is just kind of the spec, the spec sheet for our engine. And we're going to show a demo here, which is a very famous, it's based off of Quake 3. It's a very famous Quake 3 map. It's the one that shipped with the demo. And this is the acoustic mesh that we're using. So we're actually going to simulate the reverberation in real time using this acoustic, the simplified version of the world geometry right here, right? And it's about 3,000 triangles, and we're going to use about 4,000 rays to generate the resulting impulse response. But there's going to be 3 orders of reflection. So it actually ends up, the DSP load is about 12,000 audio streams, right? So this multiplies very quickly, you can tell, because our audio streams have to be simulated at full rate, 44.1, but each of them represents a reflection and not just a direct path, okay? And then we have IR filter-based material descriptions, and we'll talk a little bit about that, but maybe you can hear this. So this is quite a bit of audio, actually. When you work it all out, if you have 12,000 audio streams at 44.1 kilohertz, it ends up being about 3.7 gigabytes a second of just audio bandwidth to move it around in the system, which is quite a bit of bandwidth, but not huge compared to the GPU, which has something like 200 plus gigabytes per second of bandwidth. So the GPU turns out to be quite a good application for this, and I'll just show you this demo.
Hi, I'm here to give you a quick talk on our GPU accelerated audio engine. Right now, I have Quake 3 Arena running with the standard OpenAL audio. You can hear that the level of interaction between sound effects and the environment is pretty minimal. You'll also notice that my voice is being sent through the audio engine. This represents what you would hear over the network in a voice-over IP system such as Xbox Live. So let me go ahead and switch to our engine. Right away, you should be able to hear a big difference. My voice drastically changes depending on where in the room I am. If you listen carefully, you can tell whether I'm in a small enclosed area or a wide open area. You can tell that there's a wall on my left side here. Or that I'm backing into a wall as I'm shooting this weapon. The engine does this by keeping a simplified version of the world geometry and using that to compute reflections in real time on the GPU using ray tracing. In this particular example, up to 4,000 rays are being computed at 3 orders of reflection on the GTX Titan. In addition, each ray is individually filtered over a head response transfer function. This allows for precise positional audio over headphones. This concludes our short demonstration. Thank you for listening.
Okay. So it's kind of a comparison of a standard Quake 3 Arena, which is, you can tell actually, if you listen carefully, you can tell that the source sound effects are quite lo-fi, right? They're actually 22 kilohertz sounds from 97 or whatever they were working on this game. But you can hear that when it's really being passed through the engine, and it's really being passed through the geometry and all the material descriptions and so on and so forth. And so you can hear there's a big difference, hopefully. Okay, so let's just kind of overview a little bit about, this is a DSP seminar. I want to just kind of give you a general idea of how to map the DSP problem onto the GPU, which is really going to be a big deal, in this next couple of years. But it's not already kind of the biggest deal in terms of compute right now. I mean, you literally have a supercomputer worth of computation if you can map your problem to this particular model for less than $1,000. This is so what we're running the acoustic simulation on is this Kepler superscale architecture. That's not the newest generation Nvidia stuff. The Maxwell is their newest generation, but in terms of compute, the Kepler is still higher number of pure ALUs, pure compute power. And so the way this works is, so this is what we call the single SMX, which is the what is that, streaming multiprocessor extended for the Kepler architecture. Okay, and the highest end video card, the highest end GPU, which is the GTX Titan right now, has 15 of these cores, right? So each of these is kind of like a core in your i7 or whatever. There's 15 of them on the highest end device. And this is a superscalar device. You can tell that they're, multiple dispatch units and schedulers on top, right? And each of those dispatch units and schedulers schedules a warp, which is a group of threads, and we'll talk about that in a bit, into basically one column of these green guys, right? And one column of those green guys, you can think of that as a sort of a SIMD grouping. So if you have a bunch of stuff that operates on sequential data or operates on data with a fixed stride, which is in this case this kind of ray tracing and kind of parallel DSP, then it can be scheduled to essentially one column of these single precision floating point units, which are those green blocks. And that you can tell kind of makes up the majority of this device, right?
Are those 192? Are those each 192 parallel data points, or are those are they subdivided below that?
Okay, yeah, so they're actually subdivided in a really weird way. So what happens is each of these guys is essentially a warp, right? Mm-hmm. And a warp is the minimum scheduled unit, right? And so that's like one column, and I don't know what that is. That's like it looks like 16. I think that's 16 of the cores. Okay, and so that basically a warp has to be coherent in terms of data, just like a traditional SIMD architecture. But between the warps, it doesn't have to be, right? So you can have, as long as you don't have significant branches within the warp, you're okay in terms of performance. It's so as long, because if you take a look up there, right, there's 4 independent warp schedulers, and there's 8 dispatch units, one for every column essentially. And it's actually really strange because there's 2 dispatch units, right, for 3 warps worth of processing, and that's because it takes more than one cycle for every time it dispatches a group of instructions. Okay, but yeah, so your data point is actually, your minimum schedule unit is really a thread, right, which is one data point. But for optimal performance, you want that at least this warp, which is one column, to be coherent. Okay, so you want to treat it as a 16-way SIMD machine that also has, 1, 2, 3, whatever that is. I think it's 8 times. There's one more, so it's 12. There's 12 columns there, so it's 12-way superscalar 16-way SIMD machine. So each of these cores. And the way this works in software is this ends up looking like this, right? So we have these threads which map to the atomic data point, right? That's like that's your absolute, your smallest data point, whether that's a pixel, whether that's a ray, whether that's a vertex, or so on and so forth, depending on what your problem is, or a sample. That's your smallest parallelizable unit. You group these parallelizable units into blocks, okay? And the GPU actually, the scheduler automatically partitions this block into warps, okay? But this block exists because not necessarily for execution, but for memory sharing. So threads within a block can share data within each other at a high speed because there's a shared memory here that exists within the block, okay? So usually what this block is, for example, if I have pixels, these are pixels that are close to each other. If I'm doing some kind of graphical FIR filtering, for example, clearly these are pixels that are within kind of the span of the size of my image filter, right? Because they need to be able to share data with each other, okay? And so all these warps together form the grid, all these blocks together form the grid, and the grid is the span of my problem. So if I'm doing like an FIR filter for an image, that's my image, right? That's my source and destination image, okay? And so important things, in fact, I have a slide right here. This is kind of the approach I want for doing any kind of GPU mapping for any sort of problem, but especially for a DSP problem. Okay, so we want to identify parallel segments of the problem. So that's whether that's a pixel, that's a sample, so on and so forth. What is the smallest thing that we can independently process without necessarily a bunch of communication for other things? And that goes right into one of these threads. Okay? So for example, if it's image processing, clearly we want a thread to be, want to assign the finest grained parallelizable unit to a thread. And then we want to identify groups of thread that require communication with other threads for some reason, right? And if you have a filter, well, you kind of need to be able to operate on the locality of where your filter is moving through, right?
So we don't need to actually run exactly the same filter on every ray within the thread. We just need to be sharing data that constructs the filters
Exactly.
for each of the threads.
Yeah. So it just, right, you can read once in, and basically the idea behind this block, this higher order abstraction right here, is this big shared memory, right? And the fact that it maintains the state of each thread within the block. What's really going on here is quite complicated, actually, because what's really going on is the GPU is breaking up these threads into individual schedulable units, which are smaller than a block, but larger than one thread, right? And it's dynamically taking a look at every dispatch unit is dynamically taking a look at which one of these columns is free to do something. And it's stuffing one of those warps, as they're called, schedulable units, into that column, right? So that's why we have to be careful about what we want to call a block, because we have some constraints to what we call a block. The block maintains the state. Outside of the block, there is no state for an individual thread, right? So because it has the register file. So we have to, we have to be careful about how many threads we want to assign to a block. And that's a variable, that's a parameter that we can say. We can say, okay, well, assign 16 threads to the block, or assign 32 threads to the block. And the compiler will try to do that if it has enough registers, if it has enough shared memory, so the GPU resources essentially do that. And so then we want to take a look at, make sure our memory space is compatible with what we're trying to do, right? So if we have to pass data from one thread to another, well, that probably has to be in shared memory, right? We can think about ways to do that outside of shared memory, but it becomes extremely expensive, and you might have bottlenecks there. So we have to make sure that we have appropriate memory spaces, and then we have to make sure that whatever we've chosen here doesn't violate the actual physical limits of the GPU. How many registers does it actually have? Right? How much state can it maintain for each of these threads? If all your threads are keeping a bunch of state, for example, within the thread, and they need a bunch of registers, well then there's not many threads that you can assign to that block. So it just ends up being a trade-off.
Are there groups of warps that would have shared memory space across
so
they stay within the warp, right?
Yeah, so it's weird because even though the warp is the minimum schedulable unit, they're all assigned to the same SM. So right, so like this is kind of the strange disconnect. Is like this shared memory is actually the shared memory right here for the whole SM, right? So even though this warp executes as a unit, they all have access to the shared memory. And there's some strange banking that actually does happen, because intuitively you can think, okay, well maybe these guys, there's 192 of these guys, they probably can't all write to the same shared memory at the same time, right? And they can't. And there's internal banking of this shared memory that actually is divided to individual warps. But
so there's no hierarchy of that where one group of 4 warps has a
right,
local
has a
shared
slice.
banking.
Yeah.
It's scheduled in some way.
It's scheduled in some way.
At a global level.
Yeah, or at a SM level, right? There's also 15 of these, but we try not to think about the fact that there are 15 of these, except when we deal with L2 cache and things like that. This is really, we think of this as the size of our unit, and then the grid is just a bunch of these put together.
So so any access to shared memory has the potential to be on the order of 1/12 as slow as access to the state within the warp, because it's competing with 12 other warps to communicate with the shared memory then, because there is no, okay.
Yep, and yeah, exactly. It's coalesced within, it's wide enough to accommodate like a write or a read from everybody within the same warp, right? But you're right, it's shared within the guys who are also, part of the same SM. So at worst, your shared memory is 1/12 slower than registers, right? At best, it's exactly the same speed as registers if he's the only guy hitting shared memory. But yeah, notice that this register file is really huge, right? If you actually work out 65K divided by 192, that's an absurd number of registers. But it doesn't really work like that, right? Because it's expected that some of these are busy at any one time. For example, they're stalled, right? They have to maintain state while another warp gets scheduled into that column. So in practice, the register file is much larger than you think it should be, right? Because 64,000 divided by 192 is an absurd number of registers, right? And most threads use 10, 20 registers at the max. Yeah, but also notice that load store and load store, right? There's significantly fewer load store resources into global memory than there are compute resources. Okay, so we're going to talk a little bit about the geometry engine here. And it's pretty weird because there's a sort of a traditional way to do geometric acoustics for designing concert halls and things like this. And the way we do it is not that. so just kind of a primer here for, if you haven't taken acoustics in a while. So generally, we want to generate an impulse response that looks something like this, right? We have the direct sound, which is the shortest time of arrival to, let's say this is the source and this is the listener, and the source happens at time is equal to 0, right? That sound takes a while to travel to the listener, so that's our delay for the direct sound, okay? So it's usually the loudest, it's the shortest time of arrival, so on and so forth. And then we have these discrete early reflections, right? These are going to tell you a lot about kind of the size, about the local positioning, like how close are you to walls, for example. And these correspond to things which are like very low order bounces, right? So like, this is in a shoebox room, like there's going to be 4 walls and there's the floor and the ceiling, right? If you consider this a 3-dimensional room we're looking at from the top. And so there's going to, without this barrier being here, there's going to be 6 first-order reflections, one off of each wall at precisely one place, if we only consider perfectly specular reflections, right? And then, once we get out of those early reflections, as we wait a longer time, well, we're getting higher-order reflections, but we don't really want to consider those as individual reflections necessarily. Right? We could do that, but really what happens is a lot of the individual bounces are not specular because they hit materials which are rough compared to the wavelengths, so on and so forth. And then there's a lot of edge diffraction going on if you have barriers inside the room, so on and so forth. And we consider, this is what we call kind of the reverberation. We consider the sound field here past a certain time to be a diffuse sound field. Right? So it exists everywhere, within that room, approximately the same. So as we, let's say, move the listener, let's say this guy's just pinging constantly, right? He's an impulse generator, he's just generating impulses. What we expect to happen, as long as we stay in the same room, this stuff is going to stay mostly the same, at least statistically. This stuff is going to shift around, and the direct sound is going to move farther and closer depending on our distance to the source, okay? And what's really going to be important is this, first of all, how long the direct sound is, like to the early reflections, right? That's going to tell us a lot about how far, the general shape of the room and how far we are from the source and so on and so forth. And the length of this reverberation, right? And that's going to tell us the characteristics of the room, irrespective of our position. Like, this is going to be the same as we move, or at least statistically similar, as we move the listener around the room. And the length of this, the time that it takes for this tail to drop, for example, 60 decibels below the direct sound, well, that's going to tell us a lot about the overall size of the room. Okay, so the usual way to do this is to is to do what we call a forward ray tracing, right? So we have the source here, we're like emitting a bunch of rays. And we're catching a couple of rays that happen to end up at the listener, okay? And that's kind of the traditional statistical, if you want to run a statistical geometric acoustics model, that's kind of the traditional way to do that. The problem with doing that approach is that you have this detection issue, right? Most of your work is going to be wasted because in practice, very few of your rays are going to go from the source to the listener. It's very hard to find those exact paths, right? In a shoebox room like this one is, you only have 6 of them. And depending on what you allow for that cone of error, right, you could have anywhere between 0 to 6. So what we do is instead, we do a model that's really inspired by computer graphics. And what we do here is we start shooting rays out from the listener. And we just look at the first thing that it hits, okay? And what we then generate is we generate 2 approximations. We say, okay, well, let's say it's hitting here. We generate a probe ray to the source, and we see, does this point have a direct line of sight to the source or not? Okay. If it does, then we want to evaluate how perfect that reflection is to the source. If it doesn't, as in this case, where it's occluded by this barrier here, then we say, okay, well, at this point, the audio energy is occluded from the source, right? And then we make a perfect reflection from that first intersection point, and we keep doing this process. And what we're essentially doing is we're sampling various walls around the listener and looking at how much of a perfect reflection these various walls are getting from the source. How much visibility are these various walls that are close to, the listener getting from the source? Okay? So really this is kind of the so-called Lamberton reflection model, right? Where we're looking at, well, for example, right here, this is the second order reflection, and it's fairly perfect as compared to the source in this case, right? The dot product between the perfect Rayleigh reflection here versus this S2 vector is pretty close to 1. So our intuition is that this wall catches quite a bit of acoustic energy from this source if we're considered in this direction.
So you essentially, in addition to the rays that you've shown here, you draw another ray that follows the S2 line.
Yes.
That's just decreased in amplitude by cosine of theta or by some Lambertian function like that.
Yeah. Mm-hmm. And so this is kind of the standard way to do ray tracing in computer graphics, and it really relies on this Lambertian approximation, right? Because they have the same problem in computer graphics. What are the chances that you come up with all these rays that exactly hit the source in a perfect way? And so you have to recycle that data that doesn't give you a perfect reflection, but maybe gives you close to a perfect reflection. Well, let's weigh it less instead of weighing it 0.
So when you say that you have 4,000 rays that are each taken out to 3 bounces, then effectively you're getting information from the source up to 12,000 times.
Yes.
At each bounce, you might get some information from the source.
Exactly.
Okay.
Right. So we have 12,000 audio paths, and that's where it gets expensive, right? Because we really have 12,000 DSP lines that we have to deal with. And so this actually is handled extremely quickly using Nvidia's libraries, because the Nvidia libraries are super great at doing this thing. And what we actually do is, of course, each ray is then assigned to a thread, and then there's almost no communication between individual threads because rays are essentially independent. Whether one ray hits or not doesn't really change the outcome of another ray. And they're just independently colliding against the world, right? And any questions about this?
Okay.
Yeah.
At the destination of S, is a sound array from S2 or a mixture of S2 and S3?
Yes.
The intensity at S is only single one from S2 or a mixture of S2 and S3?
These like, you're right. So your intuition is like, aren't these amplitudes just like going infinitely smaller, right? Because this guy's already attenuated from this, right? And is he further attenuated from that? Yeah, and that's true. And we have to have a hack to take care of that. Otherwise, these amplitudes very quickly fall off, right? Because they fall off to 0 very quickly. Because let's say this guy, he's occluded at this point. So you're saying, well, anything past that is weighing very little. Well, we don't want to do that, right?
Well, you've got two different echoes being added together there, right? You've got the S1, which is essentially 0, but you've also got the balance, which is at almost full amplitude.
And so this is at almost full amplitude. And actually, this is a kind of a mistake. This should be S2. But this should be S2, and let's say that's S3. So so this guy here, he's evaluating something that's probably also occluded from here, but he does have full visibility into whatever this point is. Okay.
So you're occluding, you're scaling down each individual path, but then you're adding paths together. So you can come back with a fairly high amplitude.
Yeah, but you still have to be careful because this is clearly not energy preserving, right? Like, actually what's happening here is if you're saying this is kind of a diffuse reflection, right? Really what you have to do is account for a bunch of other rays that are scattered in random directions or some radiation pattern, and then sum all those together, right?
But each of those specular reflections will have a pretty high reflection coefficient.
Yes.
They'll be 0.5 or 0.9.
0.5 on that, exactly. Material. And so depending on the material, that will work pretty well.
And how such large number of arrays are generated randomly or?
Oh yeah, so we have a scale pattern. So we
random
we tessellate. Yeah, so we started with a random pattern, and then we scaled it to the right number of points by removing a certain number of points. And so it actually is problematic because if your sampling is very regular, you get really strange aliasing effects. Because you can move across a door a little bit, like if you just use spherical coordinates or something, you just sample regularly on a spherical grid, it doesn't work very well, right? Because you can lose a whole bank of rays, a whole phi of rays or whatever that is, as you're moving your character around, and so that causes a lot of problems. That's a good question. Okay, so this is really just kind of reiterating the effects of the previous slide. But one thing is, so there's another group that's doing very similar things at North Carolina, and what they do is they're still intent on finding exact paths because they're not using the GPU. So anytime you don't use the GPU, it behooves you to find exact paths because you have fewer signal processing chains, right? Right now we have 12,000 signal processing chains. That's prohibitive to do in real time on the CPU. So what they're doing is they're actually, it's actually pretty clever. So what they do is they do the standard forward ray tracing, and maybe they have some tolerance, but maybe within a frame time, let's say 20 milliseconds or whatever, or 80 milliseconds, 50 milliseconds, whatever you want to call your frame time is, they can only find one exact path, right? So what they'll do is they'll hang on to that one exact path, and then they'll just keep every other frame, well, your player moves a little bit, your sound sources move a little bit, but chances are that exact path is still correct. Like they'll tag the triangle that path hits, and then they'll say, okay, well, just check if this path is still valid, and try to find me another path. And so they'll keep doing that, and assuming your player character is moving slowly, you'll eventually build up a whole set of paths. See, that's the other way to do this, because you can make assumptions about how slow your characters are moving.
You track the movement of the game player.
Right, because they don't move that fast, right? If this wall is represented by one triangle or two triangles, I can move all the way over here.
So the paths can be reused.
The paths can be reused. So that is one way to, in real time, find the exact path. And I thought that was pretty clever. The problem is their reverb sounds really thin because they still only have exact paths, right? It's very difficult it's very difficult to build on top of that. Once you've found all the first order, second order, third order paths, you still only have, you know, a couple dozen taps in your filter, and it just doesn't sound very good, right? But I thought that was clever.
These 12,000 rays, and then along each one of them, you build up what is the filter by the IIR filtering at each bounce. And
and so we actually don't have enough bandwidth to do 3 times, so we just do the one that's closest to the.
Okay.
Right. So like the first order ones, it actually has 1 filter for the material. Like the second order one just filters the closest guy.
Where do you get the material filters from?
We just make them up.
make up something that sounds
it sounds pretty good.
What wood should sound like?
Yeah.
What concrete should sound like?
It actually works pretty well. You know, you can look up some numbers for frequency response of various, you know, like pure specular reflections. It's pretty strange. Like all that data, when you put it together, doesn't actually sound that great. Because a lot of that is more. Our filters are really simple, right? They're just first order IR filters. A lot of those are kind of strange tables that don't map very well to first order IR filters, or you know, biquad filters, second order IR filters, right?
Yeah.
And so a lot of those just kind of, you can sort of approximate that. You can use pronies, you can use all kinds of tricks to sort of approximate that from the data that you actually have. It ends up being pretty strange when you do, right? Because the problem with pronies is like, unless the system that you're trying to identify is actually the system that your model accounts for, the rest of those poles are just like crazy, right? Like you're unconstrained past outside of that point. Like if the physical process that's generating that impulse response is more complicated than your model is saying that it is, right? Pronies does something crazy, you know, because it really is just matching like the poles that it can. Right, does that make sense?
Yeah, because I guess the reason that you have this frequency shaping with materials is what you were saying in the beginning, that the texture of the material is large at the frequencies of some sounds.
Exactly, at some frequencies.
Which is an FIR effect, not an IR effect.
Exactly, and so
within the micropores.
Yeah, exactly. You're convolving there at that very point. So if you're really approximating with an IR filter, it's not as simple as just.
You can't just go and say this frequency characteristic that I looked up in this architectural handbook has a certain frequency center and bandwidth.
Right.
That's not enough.
That's not really enough.
Huh.
And so it's better to just say, you know, and a lot of these things, especially if you're doing games, it's a lot easier to say, you know what, I'm just going to make the world kind of cartoony, a little bit exaggerated. It's not a problem because you expect it to be cartoony anyway. The rest of the graphics are cartoony, right? So as long as you get approximately that effect, it's like, oh, this room sounds really metallic, or oh, this room sounds really dampened. I think this is a false wall because there's a weird filtering effect, you know, or it's resonant or something like that. Like you get those effects, and that's really all you can ask for, is just saying, okay, well this feels like drywall because it's a little bit resonant or something like that. And so this is kind of our first order. This is just a neat effect that no other system really has. So we have 2 cameras set up. We have a sound source that's kind of on stage. This is a very old version of the software. And this is kind of an approximation. So we have listener 1, which is in the center of the room. And we expect that, you know, if you're in the center of the room, that frequency response is fairly flat because most of those paths are pretty randomly distributed at most wavelengths, right? And then if you have listener 2 who's really in the corner, well, you can imagine that the paths that are really going to affect listener 2 are the ones that are bouncing off of these walls that he's very close to. But those all have almost the same length, right? Those paths almost have the same length to the source. So we expect that at some frequency, listener 2's, you know, response is going to explode because you're going to have some kind of constructive and destructive interference at some frequency, right? This is kind of just sort of basic checking. And this is just, we isolated the second order, first order reflections, and we just wanted to take a look at what that looks like. And we actually sent a chirp through the thing. So this is actually deconvolving as if it was really a room, which is pretty strange. Because actually we never get the real impulse response. And I'll talk about why we never get the real impulse response. So this is kind of generating the impulse response as if this was really a room. We put in a test chirp, and then deconvolve that out, take a look at the room response here. And so camera 2, you get a little bit of strangeness in the base there, but nothing. And then and then it just gets wavy here because it's just how those things look. And then for camera 1, this is the one in the corner. You have a huge amount of bass boosting here, right? And then this is really
what's the difference between the left and right?
Yeah.
Oh, that's the left and right.
Yeah, because he's facing that way, right? So this is one is like facing the wall, I think, and this is the weird one because it looks really mobile, right?
So that's the ear that's actually toward the wall.
I think that's the ear that's toward the wall. Yeah.
Yeah. So you're getting the nulls, the alternating peaks and troughs at the where they.
Right. Yeah, where they constructively and destructively interfere.
Yeah.
You know, because the wavelength is decreasing as we go this way. Okay, so let's talk a little bit about, just quickly here, since we're kind of running out of time, we'll just talk a little bit about the performance. And the performance scales to order times sources times triangles times rays. And we can use a small triangle count, and then we use this BVH, bounding volume hierarchy, to simplify some of the ray tracing. This is actually all done in Nvidia's libraries. But the idea is, like, you know, you can tell a ray is going to miss every triangle in that box if it misses the box, right? That's the only idea there is to this BVH. So you don't have to check against every triangle in the box if the ray misses the box. Oh yeah, so this is kind of cool. So everything so far is assuming there's one source in the system. That never happens in a game, right? It's always polyphony. You always have more than one thing going on. So what we actually do is we're assuming, look, it's going to get more chaotic. The more sources you have, the less your ability to discern every individual source. So why don't we just go ahead and split up our rays in this way? We'll just, every time we have two sources, let's just steal half of the rays and trace them to our other source instead of our first source, right? And so, I mean, yeah, every individual sound has less fidelity because there's fewer reflections, but the overall audio scene still has the same number of reflections, still has the same number of paths. They're just multiplexed to different sources. And it ends up working pretty well. Okay, so this is the audio processing, and this is our key here. So we have source, our delay due to the path length. Every one of our 12,000 paths looks like this, right? There's a materials IR filter, and there's HRTF IR filter. And remember, each path we're shooting from the listener, so each path has spatial coordinates, spherical coordinates from your head, right? So every path has different different HRTF coefficients. Behavior at reflection, yeah, okay, this is not super interesting. Well, it is, but I don't have the time to go over this.
We just talked about it, I guess.
Yeah. Edge diffraction is pretty useful, actually, and you need to do something about edge diffraction, even if what you do is pretty lame. So this is what I mean by edge diffraction. At low frequencies, so I have a wedge, right, diffracting wedge. Source is over here, I'm moving the receiver over here, right? So what I expect to have is, if I'm within line of sight of the source, I get sound. If I'm behind the shadow, I don't get sound. That's what I expect to happen. What happens is, that's only true at high frequencies, right? So at low frequencies, I barely get anything, any attenuation. Okay, and then there's this crazy stuff that happens because of the diffraction model. And so what we have to do is, at least we have to not attenuate low frequencies in the same way we attenuate high frequencies. And that's all we do. We just implement a hack in the materials filter. We say, okay, well, if it's occluded, don't occlude very hard if it's low frequency sound, right? I mean, we're not interested in modeling this peak. This peak is not very big anyway. And it ends up being, you can kind of tell from looking at it, but it's like the cosine of something over the sine of something, and it depends on the wavelength and the angle. And it's a bunch of transcendental functions. This is the BTM model. It ends up being a bunch of nasty transcendental functions. But the general thing is just, look, if it's a low frequency thing, don't attenuate it very much if it's occluded, right? If you see a hallway and there's a subwoofer at the end of the hallway, even if you turn that corner, it's not going to occlude that subwoofer. So don't do it here. Yeah. So that's pretty much what we do here. And it turns out that this is really actually lucky, because your positional ability really doesn't work at low frequencies either, right? Because your head has the same problem. That, look, everything is diffracting around everything else. It's diffracting around your head. It's diffracting around your shoulders. You can't position low frequency sources anyway very well. So the net effect is, yeah, okay, the occlusion is, the source is coming from the wrong place if it's a low frequency source. But you can't tell that, right? If there's a subwoofer on the other side of this wall, in our engine it's going to sound like it's coming right through the wall. Whereas really it's diffracting around the edge, that is the door, and so on and so forth. But it's really hard to tell that with any HRTF model, because the HRTF is essentially flat at those very low frequencies anyway.
So you pick one cutoff frequency based on the HRTF, basically, based on the diffraction around the hip, and you say anything below that frequency, you'll allow it to pass through a wall.
We'll allow it to pass through,
basically.
Yeah. Because, and anyway, we have that extra filter, right? Because that occlusion filter doesn't get used, or that materials filter wouldn't get used if there was occlusion, right? So we have that extra filter. Let's just do something with it instead of just passing data through. Okay, and the final thing is this GPU mixdown. So this is, you're going to run into this problem if you do any parallel DSP work. Because at the end of the day, we have to generate a stereo stream. We have to generate a left stream and a right stream, right? So the way we do the DSP is pretty straightforward. Every thread is just, let's assign a thread one of our 12,000 paths, right? Because it maintains state within that thread. You have to keep track of the filter state, and you have to keep track of like which sample you're on and things like that. It doesn't need much data other than that. It looks up the coefficients once at the beginning of the processing. It processes a whole block, which is, in our case, 2560. It's 2048 with a bit of overlap, so we can do overlap and add on each side. So to be continuous. So it's really, it's 2048 real samples, but we have to compute 2560 in order to not have gaps in the reconstruction. And then that's pretty straightforward, right? Each thread just kind of goes through, does its own filtering, keeps track of its own state. It's happy, but then we end up with 12,000 of those that need to be collapsed into a left channel and a right channel. So how do you do that on the DSP? Well, first thing you have to look at is it even practical to do that, right? How much data is here? Well, 2560 times 12,000 times 4 is 120 megabytes per frame, okay? If we're doing 2048 samples at 44.1 kilohertz, that's 22 frames a second. So our total data is 2.6 gigabytes a second. We actually need twice this because we need to write it out and then read it back, right? So that's how much data is being, if we just store the intermediate audio and then read it back, that's how much data we need. We need like 5.2 gigabytes. Well, our actual memory bandwidth is about 300 gigabytes. So we're okay. We can still do a bunch of graphics. This is not huge compared to us. So what we do is, and this is a pretty clever thing, is these guys write out to DRAM, to global memory. They only have to write out an audio clip, right? 2560 samples. When we do the mixdown, we flip the orientation of this array so that instead, each thread handles a slice. You see, this way, when they all add together, they only have to write one sample, right? They only have to hit really slow global memory once. Well, they have to read in a coalesced way, but we can synchronize them so that they read adjacent samples. That's no problem. And then we only have to write one final output stream, right? Into two different addresses, left and then right. So that's how we do this mixdown. You're going to have to, if you do any parallel DSP, I'm almost guaranteed you have to do this kind of parallel reduction stage at the very end. And so this is going to be really important. This is kind of one of the things, and this is by far the fastest way to do this. Any questions about mixing stuff down at the end? Okay, and then yeah, we can generate. You generate about 500 milliseconds with just three orders in that room. Q3. Obviously, it depends on dimension of the room, right? So depends on dimension of the room, depends on your sampling rate, and so on and so forth. Generate about 500 milliseconds, but in practice, you know, if you have a real room, you measured it, that T60 is not gonna, you know, it's not gonna really be that until maybe a couple seconds, 3 or 4 seconds. So it's okay to put this output into an artificial reverb. We actually didn't do it for this video. It sounds quite good. Because in your usual listening environment for games, the listening environment is so chaotic that like T60 means 60 decibels down, right? That's huge, right? Like you're never gonna hear anything down 60 decibels in a game. That's just not gonna happen, right? So really, like generating about 3 or 4 orders of reflection is plenty. You know, that pretty much generates the impulse response out to where you think it should be, or where you can actually listen to in a game. And yeah, that's pretty much it. So sorry I had to rush through a couple slides, but I'll just maybe leave time for a couple quick questions.
Questions?
Do you have any demos to show what you have already worked?
Yeah, so there's that video, and there's actually, I don't know if I can run it on my laptop. You know, you could do it in real time on a laptop usually. Yeah, other than that, like, you know, that's pretty much where we're at. So what we're interested in is, you know, like, what's in the video is actually a pretty good demonstration, because you're talking, in the video, they talk through the system. And that doesn't actually happen in real life most of the time. And so you don't have that constant reference of speech going through the system that you're actually pretty used to hearing, right? Like, you know, your ears are really attuned to paying attention to speech and reverberation in speech. And it's hard to actually hear, you know, especially with those sound effects that are really artificial, it's hard to hear, like, is this more reverb or is this less reverb? I don't know, what does the raw sound like, you know? It's kind of hard to tell. But yeah, so like one of our big applications is if you're in a virtual world where there is voice over IP, like, and it's voice over IP in the system, just like that. Well, normally without a system like this, it's just chaos, because everybody sounds like they're talking at the same place, and that's not what happens in any room, right? People are spatially multiplexed by the individual impulse responses, depending on, you know, their source positions. So you have very good spatial separation in a room, but over a speakerphone you never have that. And so this is one of the problems that we're interested in solving for games, but for also for teleconferencing and those kinds of applications.
So you need to write your own game, basically.
Yeah.
I mean,
and that's what we're working
sort of
on.
what you did with Quake, right? You took the Quake demo and piped the voice over IP. What would be the voice over IP? Piped that through the system.
Yeah, and it's pretty cool to get 2 people in the voice over IP system, because you really can tell, like, someone can be like, I'm over here, which is like meaningless in a game normally, right? You can't say I'm over here in a game because that doesn't mean anything. But in this system, you can actually say, like, I'm over here, and if they're in the same room, they can tell where you are pretty easily. And they can tell even in a map like that, simple map, you can really tell, like, which room is he in? Is he in the big room, or is he in the courtyard, or is he in the connecting corridors or something? And so that's actually pretty neat. So we're basically in the process of designing a game that's using that idea, that's just kind of going to be in the dark, and it's going to use that idea of when you're talking to people, you let people around you know where you are, but you have to be really careful, because, you know, you don't know who you can trust in that game, right? So it's kind of an open world, sort of, it's like a chat room, but it's like in the dark, right? You know, you have weapons and things like that.
So how do you evaluate the simulation?
Yeah, it's really hard to evaluate.
How good it is? It's in addition to the computational speed up, just let people listen and judge?
Yeah, that's all we've had so far. It's really hard to come up with objective evaluations. You know, the typical way to do this for many architectural acoustic simulations, so if you wanted to make a roundup of all architectural acoustic software, what you would do is you would build a scale model, and build the scale model of some concert hall, or go to some concert hall and measure it, and then build this polygonal model, reduce your measurements down to some 2 or 3 slope model, right? You say, okay, well, the initial slope looks like this, and then at some point the slope switches to this, and it's, you know, it's usually a narrow a smaller slope and then a larger slope, right? And then you would do the same thing, have the software go simulate the impulse response of that, and then go ahead and compare the parameters, right? What is the first slope? Where does the first slope switch over to the second slope? What does that look like? Let's compare the parameters over to the actual recorded model. But it's pretty artificial anyway, right? Because depending on what assumptions their models are making for what you're doing, it might not even apply that they're applying this two-slope model or whatever, right?
So you could do a comparison like using an image source method to calculate calculate all of the echoes out to a certain length.
Exactly.
And find out how much of that information is the same as what you're getting.
Yeah, and then we've done that for shoebox rooms just to see like, is this crazy or is this like approximately correct? And it's pretty correct. I mean, with our model, right, instead of individual discrete reflections, you get what you would expect, kind of a Gaussian thing, right? Because you have that dot product for how specular it is. So you have these kind of humps that are centered around where the image source model would put idealized reflections. So we do that, and the modes come out as you would expect them to for shoebox models and things like that. But anything beyond that, in terms of like evaluating the whole system down to the HRTF, that's really hard to do. Because and people who have done that ran into trouble with commercial systems, because you don't know what assumptions the commercial systems are making. Like if your model happens to correlate very strongly, the model that you're judging on happens to correlate very strongly to the model that the commercial system is using, then it looks great. And if it doesn't, then you're trying to fit some parameterized model to a different parameterized model, right? It's like, what does that even mean? So, yep. Any other questions?
Cool. Thank you.
Yes. Thanks.